Right now, at this very moment, there exists a black hole so massive, so incomprehensibly large, that it defies everything we thought we knew about the limits of cosmic objects. This monster weighs approximately 40 billion times the mass of our Sunday. To put that in perspective, if you could somehow convert the entire Milky Way galaxy into a black hole, you'd need to combine it with dozens of other galaxies to match the mass of this single object. Its event horizon, the point of no return beyond which nothing can escape, stretches wider than the orbit of Neptune around our Sunday. This behemoth has a name: the supermassive black hole at the center of Holmberg 15A, a galaxy located in the Abell 85 cluster, approximately 700 million light-years from Earth. For decades, astronomers suspected that the largest galaxies in the universe might harbor correspondingly large black holes, but nothing prepared them for what they would find at the heart of Holmberg 15A. This isn't just a big black hole, it's the reigning champion, the heavyweight title holder in a universe filled with gravitational monsters. The story of how we discovered this cosmic giant involves cutting-edge telescopes, sophisticated mathematical models, and the painstaking work of astronomers who spent years analyzing the movements of stars near the galaxy's core. It required overcoming enormous technical challenges because observing a black hole 700 million light-years away is like trying to detect a grain of sand in New York while standing in Los Angeles. The black hole itself emits no light, making it invisible to telescopes. We can only infer its presence by watching how it affects everything around it. But this discovery is about more than just finding the biggest thing. The existence of such a massive black hole raises profound questions about how black holes grow, how galaxies evolve, and what happened in the early universe to allow something this enormous to form. Most supermassive black holes are millions to billions of solar masses. Holmberg 15A's black hole is tens of billions of solar masses, pushing into a regime where our theories of black hole formation and growth are stretched to their limits. The black hole didn't form overnight. It took billions of years to grow to its current size, consuming countless stars, absorbing vast clouds of gas, and possibly merging with other supermassive black holes in violent collisions that sent gravitational waves rippling across the universe. Each of these processes left traces, clues that astronomers can piece together to reconstruct the black hole's history and understand the extreme physics that govern the universe's most massive objects. Understanding Holmberg 15A's black hole also helps us understand the broader universe. Supermassive black holes aren't isolated curiosities. They're integral to galaxy evolution. They regulate star formation, influence the distribution of matter across billions of light years, and serve as cosmic fossils preserving information about conditions in the early universe. By studying the most extreme example we've found, we push the boundaries of our knowledge and test our theories under the most demanding conditions. Drop it in the comments below where in the world you're watching from and what time it is there. Now prepare yourself for a journey to the heart of the largest known black hole in existence, where gravity is so strong it warps space-time into impossible geometries, where stars orbit at speeds exceeding thousands of kilometers per second, and where the rules of physics are pushed to their absolute limits. The Discovery Night, August 1937, when Erich Holmberg found a giant. The story of Holmberg 15A begins not with modern supercomputers or space telescopes, but with a Swedish astronomer peering through a telescope in 1937. Erich Holmberg, working at the Uppsala Astronomical Observatory in Sweden, was conducting a systematic survey of galaxies, cataloguing their positions, appearances, and properties. This was painstaking work in an era before electronic detectors and computer databases. Every observation required exposing photographic plates for hours, then carefully examining the developed images by eye under magnifying glasses. On a clear night in August 1937, Holmberg photographed a region of sky in the constellation Cetus. When he examined the plates, he noticed a bright elliptical galaxy that would eventually bear his name in the catalogue he was compiling. He designated it Holmberg 15A, with the A indicating it was the brightest member of a small group of galaxies he observed in that region. At the time, Holmberg had no way of knowing that this particular galaxy harbored anything special. It looked like many other elliptical galaxies, a smooth, featureless oval of light with no spiral arms or obvious structure. Holmberg's survey was part of a larger effort in the 1,930 seconds to map the universe beyond our Milky Way. Edwin Hubble had proved only a decade earlier that galaxies existed as separate island universes beyond our own galaxy, fundamentally changing our understanding of the cosmos. Astronomers were eager to catalogue these newly recognized objects and understand their properties. Holmberg's work focused particularly on binary and multiple galaxy systems, examining how galaxies interact gravitationally with their neighbors. The catalogue Holmberg compiled between 1937 and 1950 contained 497 galaxies, each carefully photographed and measured. He published his results in 1,950 inches, a paper titled A Photographic Photometry of Extragalactic Nebulae. The work was meticulous but unglamorous, representing thousands of hours at the telescope and in the darkroom. Holmberg measured each galaxy's brightness, estimated distances, and noted whether galaxies appeared to be in groups or clusters. For Holmberg 15A specifically, he noted its classification as an elliptical galaxy and its membership in a small galaxy group. What Holmberg couldn't have known in 1937 was that elliptical galaxies like Holmberg 15A are fundamentally different from spiral galaxies like our Milky Way. Ellipticals are typically much older, having formed most of their stars billions of years ago in intense bursts of star formation. They contain little gas for making new stars and show little ongoing star formation. Their stars orbit in random directions rather than forming an orderly rotating disk. Most importantly for our story, the largest elliptical galaxies in the universe tend to be found at the centers of galaxy clusters, and they harbor the universe's most massive black holes. Holmberg 15A is what astronomers now call a brightest cluster galaxy, or BCG. These are the most luminous galaxies in their clusters, typically sitting at or near the cluster center. BCGs form through a process called hierarchical merging, where smaller galaxies fall into the cluster center due to dynamical friction and merge together over billions of years. Each merger adds stars and gas to the growing BCG, and crucially, each merger brings with it the supermassive black hole from the merging galaxy's center. These black holes can then merge together, creating even more massive black holes. In the 1,970 seconds and 1,980 seconds, astronomers began to recognize that most, if not all, large galaxies contain supermassive black holes at their centers. Evidence came from observing the motions of stars and gas very close to galactic nuclei. The stars were moving too fast to be held in place by the gravity of visible matter alone. Something incredibly massive and compact had to be present. For the Milky Way, this object turned out to be Sagittarius A*, a black hole of about 4 million solar masses. For larger galaxies, the black holes were correspondingly larger, but determining black hole masses in distant galaxies is extraordinarily difficult. For the Milky Way, we can observe individual stars orbiting the black hole and use Kepler's laws to calculate the black hole's mass directly. For galaxies millions or billions of light years away, individual stars are far too faint to detect. Instead, astronomers must use indirect methods based on the collective motion of millions of stars in the galaxy's central regions. These methods require sophisticated modeling and high-quality data, and they're most effective for the very largest galaxies where the black hole's gravitational influence extends over a large enough region to be measurable. Holmberg 15a drew serious scientific attention in the late 20th century when astronomers realized it was the central galaxy of the Abell 85 cluster, one of the nearest rich galaxy clusters to Earth, at a distance of about 700 million light-years. Rich clusters contain hundreds or thousands of galaxies bound together by gravity, and they're important laboratories for studying galaxy evolution. The central BCG in such clusters often shows unique properties, having grown to enormous size through mergers and containing the cluster's most massive black hole. By the early 2000s, technology had advanced enough that detailed studies of Holmberg 15a became possible. The Hubble Space Telescope provided high-resolution images showing the galaxy's structure in unprecedented detail. Ground-based telescopes, equipped with spectrographs, could measure the velocities of stars throughout the galaxy by analyzing the Doppler shift of spectral lines. These velocity measurements are the key to weighing the central black hole, as we'll explore in detail in later chapters. But first, we need to understand the environment in which Holmberg 15a exists, the Abell 85 galaxy cluster, AT5, the galaxy cluster hiding a supermassive secret. Galaxy clusters are the largest gravitationally bound structures in the universe, containing hundreds to thousands of individual galaxies, along with vast quantities of hot gas and dark matter. The Abell 85 cluster, where Holmberg 15a resides, is a particularly well-studied example, located approximately 700 million light-years from Earth in the constellation Cetus. The cluster was catalogued by George Abell in 1958 as part of his landmark survey of rich galaxy clusters identifiable on photographic sky surveys. Abell's catalogue was revolutionary for its time, systematically identifying 2,712 rich clusters across the northern sky. He defined rich clusters as those containing at least 50 galaxies within a specified radius, all at roughly the same distance from Earth. Abell 85 met these criteria handily, containing several hundred identified member galaxies spread across a region roughly 10 million light-years across. The cluster's total mass, including dark matter, is estimated at roughly 1 to 2 quadrillion solar masses, making it one of the more massive clusters in the nearby universe. The cluster's structure is typical of relaxed clusters, meaning clusters that have had time to settle into gravitational equilibrium after their formation. At the center sits Holmberg 15a, the brightest cluster galaxy, with a luminosity of roughly 2 trillion times that of our Sunday. The next brightest galaxies in the cluster are significantly fainter, following a hierarchical distribution where luminosity decreases rapidly from the BCG down through the next few brightest galaxies. This hierarchy reflects the cluster's formation history, where the central BCG has grown through mergers while the other galaxies have remained distinct. Between the galaxies in Abell, 85 flows an enormous quantity of hot gas, primarily hydrogen and helium, heated to temperatures exceeding 10 million degrees Kelvin. This gas, called the intracluster medium, or ICM, is so hot that it emits primarily at X-ray wavelengths. Observations with X-ray telescopes like Chandra and XMM Newton show the ICM filling the space between galaxies, with a total mass exceeding the combined mass of all stars in all the cluster's galaxies. The gas got hot through a process called gravitational heating. As it fell into the cluster's deep gravitational potential, gravitational potential energy converted to kinetic energy, heating the gas to millions of degrees. The temperature and distribution of the ICM provide crucial information about the cluster's total mass, including dark matter. X-ray observations show that the ICM is most dense at the cluster center, surrounding Holmberg 15A, and becomes progressively less dense moving outward. The pressure gradient in the gas, combined with the assumption of hydrostatic equilibrium, where pressure forces balance gravity, allows astronomers to calculate the total gravitating mass at each radius. These calculations show that dark matter dominates the mass budget, outweighing visible matter by factors of 5 to 10 or more. Abell 85 also shows evidence for past dynamical activity despite its currently relaxed appearance. Detailed X-ray images reveal subtle asymmetries and disturbances in the ICM, including a possible weak cold front, a sharp boundary in the gas where temperature and density change discontinuously. Cold fronts are thought to form when a subcluster merges with the main cluster, with the merging subcluster's gas creating a moving contact discontinuity as it plows through the ambient ICM. The presence of these features suggests Abell 85 has experienced mergers within the past billion years or so, though not as recently or violently as some other clusters. The merger history of Abell 85 is directly relevant to understanding Holmberg 15A's supermassive black hole. Each time a galaxy cluster merges with another cluster or absorbs a smaller group of galaxies, the central BCG can grow by consuming galaxies that fall into the cluster center. When galaxies merge with the BCG, their central black holes also merge, a process that adds mass to the BCG's black hole. Over billions of years and many mergers, a BCG's black hole can grow to enormous mass, far exceeding what's possible through gas accretion alone. The velocity dispersion of galaxies in Abell 85, meaning the spread in their velocities as they orbit within the cluster, is approximately 1,000 kilometers per second. This high velocity dispersion is characteristic of massive clusters and reflects the deep gravitational potential well created by the cluster's large mass. Galaxies are moving at speeds comparable to 1/3 of 1% of the speed of light, held in orbit by the combined gravity of all the matter in the cluster. If the cluster were less massive, galaxies would move more slowly. If more massive, they'd move faster. The observed velocity dispersion, therefore, provides an independent estimate of the cluster's total mass, complementing estimates from X-ray observations. Abell 85's environment has shaped Holmberg 15A in multiple ways beyond enabling black hole growth through mergers. Ram pressure from the hot ICM has stripped gas from many of the cluster's galaxies as they move through the intracluster medium. This gas stripping quenches star formation, converting gas-rich spiral galaxies into gas-poor ellipticals or lenticulars. Holmberg 15A itself shows essentially no current star formation, having long ago exhausted its gas supply. The lack of gas also means the central black hole has little fuel for accretion, making it largely dormant, a point we'll return to in later chapters. The Abell 85 cluster is also notable for hosting several interesting member galaxies beyond Holmberg 15A. These include disturbed galaxies showing tidal tails from gravitational interactions, compact elliptical galaxies that may be the remnant cores of larger galaxies stripped by tidal forces, and several active galactic nuclei where supermassive black holes are actively accreting and emitting strong radiation. Studying the full population of galaxies in Abell 85 provides context for understanding Holmberg 15a and shows how galaxy evolution in dense cluster environments differs from evolution in the field. 40 billion solar masses. Measuring the unmeasurable monster. Determining the mass of a black hole 700 million light-years away is one of the most challenging feats in observational astronomy. We can't see the black hole directly, we can't send probes to measure it, and we can't observe individual stars orbiting it as we can for the Milky Way's black hole. Instead, astronomers must use indirect methods based on how the black hole's gravity affects its surroundings. For Holmberg 15a, the key measurement is the velocity dispersion of stars in the galaxy's central region, combined with sophisticated models of how stellar dynamics work in galactic nuclei. The fundamental principle is simple. The more massive the black hole, the faster stars must orbit to avoid falling in. Just as planets farther from the Sun orbit more slowly, while closer planets orbit faster, stars closer to a galactic black hole orbit faster than stars farther out. By measuring how fast stars are moving at different distances from the galactic center, astronomers can infer the mass distribution, including the central black hole. But implementing this principle for a distant galaxy requires overcoming enormous technical challenges. First, you need a spectrum of the galaxy's central region with high signal-to-noise ratio and high spectral resolution. The spectrum shows absorption lines from stars at various wavelengths, and the width of these lines indicates the range of stellar velocities along the line of sight. Broader lines mean a larger velocity dispersion, indicating faster stellar motions. Obtaining such spectra requires large telescopes with sensitive spectrographs and long exposure times, often tens of hours of observations. Second, you need spatial resolution adequate to measure velocity dispersion as a function of distance from the center. This requires either excellent natural seeing conditions, meaning atmospheric turbulence is minimal, or adaptive optics systems that compensate for atmospheric distortion in real time. Even with the best modern instruments, resolving the central few thousand light-years of a galaxy 700 million light-years away is challenging. Each resolution element, or spatial pixel, in your data corresponds to hundreds or thousands of light-years in the target galaxy. Third, you need sophisticated dynamical models that relate the observed velocity dispersions to the underlying mass distribution. The simplest models assume the galaxy is spherically symmetric and in dynamical equilibrium, with stellar orbits having time-averaged properties that remain constant. These assumptions allow using the Jeans equations mathematical relationships between velocity, dispersion, mass distribution, and gravitational potential. More sophisticated models relax these assumptions, accounting for deviations from spherical symmetry, rotation, and anisotropy in the velocity distribution where stellar orbits preferentially point in certain directions. For Holmberg 15a specifically, the breakthrough measurement came from a 2019 study led by Kianush Mergen and colleagues, published in the Astrophysical Journal. They used data from the Gemini North Telescope in Hawaii, equipped with the GMOS instrument providing spectroscopic observations with spatial resolution of about 0.2 arcseconds. At Holmberg 15a's distance, this resolution corresponds to roughly 600 light-years per spatial pixel, adequate for probing the central few thousand light-years where the black hole's gravitational influence dominates. The observations revealed something remarkable. The velocity dispersion in Holmberg 15a's center is exceptionally high, reaching values of 350 to 400 kilometers per second. For comparison, the velocity dispersion in the center of the Milky Way is about 100 to 150 kilometers per second, and in most other galaxies, values range from 100 to 300 kilometers per second. The high dispersion in Holmberg 15a immediately suggested an extremely massive central black hole, but translating the measurement to an actual mass requires careful modelling. Mehergan and colleagues applied axisymmetric Schwarzschild orbit modelling, a sophisticated technique where you construct a library of possible stellar orbits in a given gravitational potential. Then find the combination of orbits that best reproduces the observed surface brightness and kinematic data. The gravitational potential includes contributions from stars, which you can estimate from the galaxy's light distribution, and from the central black hole, which you treat as a parameter to be determined. By varying the black hole mass and finding which value gives the best fit to the data, you determine the black hole's mass. The result was staggering: 40 billion solar masses, with an uncertainty range of roughly 30 to 50 billion solar masses depending on modelling assumptions. This made Holmberg 15A's black hole not just large, but the largest ever measured with reasonable confidence. For context, the Milky Way's black hole is 4 million solar masses, so Holmberg 15A's black hole is 10,000 times more massive. The supermassive black hole in M87, famously imaged by the Event Horizon Telescope in 2019, has a mass of 6.5 billion solar masses, making Holmberg 15A's black hole more than 6 times more massive than that. To appreciate what 40 billion solar masses means, consider that if you converted the entire Milky Way galaxies, roughly 200 billion stars, each averaging somewhat less than a solar mass, into a single black hole, you'd still only reach about 60 to 100 billion solar masses. Holmberg 15A's black hole alone is equivalent to roughly 40% of all the stars in the Milky Way. If you placed this black hole at the center of our solar system, its event horizon would extend beyond the orbit of Neptune, approximately 30 astronomical units from the center. The discovery generated immediate interest in the astronomical community. Papers with alternative black hole mass estimates using different techniques and assumptions were published within months. Some authors argued for slightly lower masses, around 30 billion solar masses, while others confirmed values near 40 billion. The range of estimates reflects the genuine difficulty of the measurement and the sensitivity to modelling assumptions, but all analyses agreed that Holmberg 15A hosts an ultramassive black hole pushing the boundaries of what theory predicts should be possible. The 2019 kinematics study that changed everything. The paper by Mehergan and colleagues, titled "A 40 billion solar mass black hole in the extreme core of Home 15A, the central galaxy of Abell 85," represented the culmination of a multi-year effort to understand one of the universe's most extreme galaxies. Published in the Astrophysical Journal in December 2019, the study combined cutting-edge observations with state-of-the-art dynamical modelling to arrive at its groundbreaking conclusion. The work provides a case study in modern observational astrophysics, showing how astronomers piece together evidence from multiple sources to reach conclusions about objects billions of light-years away. The observational campaign used the Gemini Multi-Object Spectrograph, or GMOS, on the Gemini North Telescope in Hawaii. Gemini North is an 1-meter telescope, one of a pair of identical telescopes, operated by an international partnership. The GMOS instrument can obtain spectra of extended objects, like galaxies, with spatial resolution determined by the seeing conditions and by the size of spatial pixels in the detector. For the Holmberg 15A observations, the team achieved spatial sampling of approximately 0.2 arcseconds per pixel, allowing them to map velocity dispersion across the central region of the galaxy. The observations were conducted in Q mode, where telescope operators execute the observations when conditions meet specified requirements, rather than requiring the science team to be present at the telescope. This mode is efficient for programs requiring specific weather conditions. For Holmberg 15, a good seeing with minimal atmospheric turbulence was crucial to achieve the needed spatial resolution. The total exposure time was substantial, accumulating several hours of on-target integration to build up sufficient signal-to-noise in the spectra. The resulting two-dimensional spectra showed absorption lines from stars throughout the central region of Holmberg 15A. These lines arise from elements like calcium, magnesium, iron, and sodium in stellar atmospheres. When many stars with different velocities contribute to a spectrum, each star's absorption lines are Doppler shifted by an amount proportional to its velocity along the line of sight. Stars moving toward us have blue shifted lines, while stars moving away have red shifted lines. The combined spectrum shows broadened lines, with the line width indicating the velocity dispersion, the statistical spread in velocities. Mehrgen's team measured velocity dispersion as a function of position across the galaxy center, creating a two-dimensional map of stellar kinematics. The dispersion was highest at the very center, exceeding 400 kilometers per second, and decreased moving outward. The radial profile of velocity dispersion, showing how it changes with distance from the center, provides the key constraint on black hole mass. A more massive black hole produces higher central velocity dispersions because stars must move faster to remain in orbit. But extracting a black hole mass from velocity dispersion measurements isn't straightforward. You need a detailed model relating kinematics to mass distribution. The team used Schwarzschild orbit modeling, a technique named after Karl Schwarzschild, who made fundamental contributions to understanding orbits in gravitational fields. In this method, you specify a gravitational potential, including the black hole mass, as a free parameter. Then calculate a large library of possible stellar orbits in that potential. Each orbit is characterized by its shape, orientation, and energy. You then find the combination of orbits that, when combined, reproduces the observed surface brightness and velocity dispersion. This is done by assigning weights to each orbit and adjusting the weights to minimize the difference between model predictions and observations. The black hole mass is varied systematically, repeating the orbit modeling for different masses until you find the mass that provides the best fit to the data. Statistical techniques determine the uncertainty in the derived mass. The modeling revealed that a black hole mass of 40 billion solar masses provided the best fit to the Holmberg 15A data. Models with significantly lower masses, say 20 billion solar masses, produced central velocity dispersions lower than observed. Models with significantly higher masses, say 60 billion solar masses, produced dispersions higher than observed. The uncertainty in the measurement, typically quoted as 1 sigma errors representing 68% confidence intervals, ranged from about 30 to 50 billion solar masses, depending on modeling assumptions. One critical assumption in the modeling is the mass-to-light ratio, the ratio of mass to luminosity for the stars making up the galaxy. If stars are systematically more massive than assumed, the total stellar mass is higher and less mass is needed in the black hole to explain the kinematics. Conversely, if stars are less massive, more black hole mass is required. The team tested a range of mass-to-light ratios consistent with stellar population models for old elliptical galaxies and found that while the exact black hole mass value depended on this assumption, all reasonable choices yielded masses in the tens of billions of solar masses. Another important consideration is the orbital anisotropy, describing whether stellar orbits are predominantly radial, predominantly tangential, or isotropic with no preferred orientation. Different anisotropies produce different velocity dispersion profiles for the same mass distribution. The Schwarzschild modeling includes anisotropy as part of the model to be determined from the data, but degeneracies exist where different combinations of black hole mass and anisotropy can produce similar fits. The 2019 study represented a major advance over earlier work on Holmberg 15A. Previous studies had noted the galaxy's unusual properties, including its very large core and low central surface brightness, suggesting an extreme central black hole. But earlier black hole mass estimates were crude, based on indirect scaling relations rather than detailed dynamical modeling. The Mergen et al. Study provided the first robust model-dependent mass measurement using state-of-the-art techniques. Stellar velocity dispersion. How star movements reveal black hole mass. Velocity dispersion is a statistical measure quantifying the spread of velocities in a population of objects. For stars in a galaxy, velocity dispersion tells us how much the stellar velocities vary around the mean velocity. If all stars orbited in perfect lockstep at the same speed and direction, velocity dispersion would be zero. In reality, stars have different velocities due to their different orbits, and the dispersion measures this diversity. Mathematically, velocity dispersion is the square root of the variance of velocities, closely related to the standard deviation in statistics. In the context of measuring black hole masses, velocity dispersion serves as a proxy for the gravitational potential. Stars in a deeper gravitational potential, meaning a location where gravity is stronger, must move faster to avoid falling in. Near a massive black hole, gravity is very strong, so stars have high velocities, and the velocity dispersion is correspondingly high. Farther from the black hole, gravity weakens, velocities decrease, and dispersion drops. By measuring how velocity dispersion changes with position, astronomers map the gravitational potential and infer the mass distribution. The technique works because of the virial theorem, a fundamental result in classical mechanics relating kinetic energy to potential energy for systems in gravitational equilibrium. For a self-gravitating system in steady state, the time-averaged kinetic energy is proportional to the time-averaged potential energy. Velocity dispersion is related to kinetic energy, and potential energy depends on mass distribution. The virial theorem provides a mathematical relationship, allowing us to deduce mass from velocity measurements. For a simplified case of a spherical system with isotropic orbits, the relationship can be written approximately as mass equals a constant, multiplied by the square of the velocity dispersion, multiplied by the radius, and divided by the gravitational constant. Here, the mass represents the total mass enclosed within the system. The velocity dispersion refers to how fast the stars or particles are moving in different directions. The radius is the distance from the center, the gravitational constant determines the strength of gravity, and the constant k is a number close to 1 that depends on how the mass is spread out. This shows that mass scales with the square of velocity dispersion and linearly with radius. Doubling velocity dispersion increases the inferred mass by a factor of 4. Measuring velocity at twice the distance also increases inferred mass by a factor of 2 if velocity dispersion remained constant. Real galaxies are more complex than this simplified case. They're not perfectly spherical, orbits aren't isotropic, and the system may not be perfectly relaxed. Modern analyses use sophisticated models accounting for these complications. The Jeans equations provide a more general framework relating velocity dispersion to mass distribution without assuming isotropy. These are partial differential equations describing the dynamics of a collisionless stellar system, where collisionless means stars interact only through gravity and don't physically collide. Solving the Jeans equations requires specifying the velocity distribution function, which describes how many stars have each possible velocity at each position. Different choices for this function correspond to different orbital structures. A common simplification is to assume the velocity distribution is Gaussian, meaning velocities follow a bell curve. This assumption is reasonable for many systems, but can be relaxed in more sophisticated models. The observational challenge in measuring velocity dispersion is obtaining spectra with sufficient signal-to-noise ratio and spectral resolution. Signal-to-noise ratio measures how much stronger the actual signal is compared to random noise. For faint galaxies, or faint regions within galaxies, noise can be substantial, making weak absorption lines difficult to detect. Spectral resolution, measured in angstroms or kilometers per second, determines how precisely you can measure line widths. Higher resolution allows detecting smaller velocity dispersions. For Holmberg 15A at 700 million light-years distance, even though it's one of the brightest galaxies in the universe, the central region's surface brightness is relatively low due to the large core, making observations challenging. The team needed multi-hour exposures to achieve signal-to-noise ratios of 50 to 100 per angstrom, adequate for precise velocity dispersion measurements. The spectral resolution of GMOS, approximately 100 to 200 km per second depending on configuration, was sufficient to resolve the velocity dispersions of several hundred kilometers per second. Another subtlety in velocity dispersion measurements is the template mismatch problem. To measure velocity dispersion, you compare observed spectra to template spectra of stars with known properties. Any mismatch between the template and the actual stellar population in the target galaxy introduces systematic errors. For old elliptical galaxies like Holmberg 15A, the stellar population is dominated by red giant stars and evolved stars, and appropriate templates must be used. The Megan team used stellar population synthesis models, specifically calculated for old, metal-rich populations. The core deficit, a 15,000 light-year hole where stars should be. One of the most striking features of Holmberg 15, visible even before the black hole mass measurement, is its enormous stellar core. Galaxy cores are central regions where surface brightness, the amount of light per unit area, decreases toward the center rather than continuing to increase. Most elliptical galaxies show steadily increasing brightness toward the very center, following what's called a Circic profile, or, for the central region, a power law. But some galaxies, particularly the most massive ellipticals, show cores where the central brightness is depleted. Holmberg 15A's core is one of the largest ever observed, extending roughly 15,000 light-years in radius. Within this core, the galaxy contains far fewer stars than would be expected if brightness continued following the trend seen at larger radii. The core's size is about twice the radius of the Milky Way's stellar disk, making it an enormous region by galactic standards. If you measured the mass deficit, the difference between the actual stellar mass in the core and what would be expected from extrapolating the outer profile inward, you'd find that several billion solar masses worth of stars are missing from the core. The formation of cores in massive ellipticals is intimately connected to supermassive black hole binaries and mergers. The leading theory, called core scouring, proposes that cores form when two supermassive black holes merge after a galaxy merger. In the final phases before merging, the two black holes form a gravitationally bound binary, orbiting their common center of mass. This binary interacts with stars passing nearby, transferring energy from the binary to the stars in a process called three-body interactions. During a three-body interaction between a binary black hole and a passing star, the star's trajectory is deflected by the binary's gravity. The deflection changes the star's energy and angular momentum. In a typical encounter, the binary shrinks, losing orbital energy, while the star gains energy and is scattered to a higher orbit or even ejected from the galaxy entirely. Over millions of such interactions, the binary can eject or scatter a substantial population of stars from the central region, creating a depleted core. The size of the resulting core depends on the masses of the merging black holes and the time they spend as a binary before merging. More massive binaries scatter stars more efficiently and create larger cores. Binaries that survive longer before merging have more time to scatter stars and thus create more extensive cores. For Holmberg 15A's 15,000 light-year core, models suggest the progenitor black hole binary had a combined mass comparable to or even exceeding the current 40 billion solar mass black hole mass, and that the binary survived for tens to hundreds of millions of years before finally merging. Observational evidence supports the core scouring scenario. Surveys of elliptical galaxies show a correlation between core size and galaxy mass, with more massive galaxies having larger cores. This is expected because more massive galaxies host more massive black holes, which create larger cores. There's also a correlation between core size and black hole mass directly. Galaxies with larger cores tend to have more massive black holes, as expected if core formation and black hole growth are linked through mergers. Holmberg 15A fits these correlations but sits at the extreme end. Its core is among the largest known, and its black hole is among the most massive. This suggests Holmberg 15A's formation involved particularly dramatic mergers, possibly including the coalescence of two already massive black holes, each weighing tens of billions of solar masses. Alternatively, multiple successive mergers, each involving somewhat smaller black holes, could progressively enlarge the core. An alternative theory for core formation invokes stellar dynamical processes without requiring black hole binaries. In this scenario, the core forms gradually over time as stars interact gravitationally with each other and with the central black hole. These interactions transfer energy between stars, causing some to sink toward the center and others to move outward. Over billions of years, this process could, in principle, create a core. However, calculations show this mechanism is inefficient and produces much smaller cores than observed unless extreme conditions prevail. For cores as large as Holmberg 15A's, the binary black hole scenario is strongly favored. The distribution of stars within the core provides additional clues to formation mechanisms. Observations show that the stellar population in cores isn't completely absent but is depleted and shows unusual kinematics. Stars in the core often have anisotropic velocity distributions, preferentially moving on radial orbits that plunge toward the center and back out. This anisotropy is a signature of gravitational interactions that preferentially scatter stars onto radial orbits, while ejecting or scattering stars on more circular orbits. Recent simulations of binary black hole evolution in galaxy mergers have reproduced cores similar to Holmberg 15A's. These simulations use n-body codes tracking the gravitational interactions of millions of particles representing stars and dark matter. The simulations show that binary black holes can indeed scour large cores on timescales of hundreds of millions of years. The cores then evolve slowly over subsequent billions of years through stellar dynamical processes, but the basic core structure remains imprinted by the binary phase. Measuring these cores requires sophisticated observational techniques. Astronomers use high-resolution imaging from space-based telescopes like the Hubble Space Telescope to map the surface brightness distribution across the galaxy. The challenge lies in detecting the subtle flattening of the brightness profile at the center, which requires precise photometry and careful subtraction of background light and foreground stars. For Holmberg 15A, observations must penetrate through the glare of surrounding stars and the diffuse light from the galaxy itself to reveal the depleted core structure. Spectroscopic observations complement imaging by measuring stellar velocities within the core, providing information about the orbital structure and mass distribution that helps constrain formation models. Comparing Holmberg 15A to other galaxies with large cores reveals important patterns in galaxy evolution. The most prominent comparison is with M87, the giant elliptical at the center of the Virgo cluster. M87 hosts a black hole of roughly 6 billion solar masses and has a core extending several thousand light-years, substantially smaller than Holmberg 15A's, despite M87's fame and prominence. This difference underscores how exceptional Holmberg 15A truly is. Another notable comparison involves NGC 6166, the central galaxy of the Abell 2199 cluster, which has a core comparable in size to Holmberg 15A's and likely underwent similar merger history. These comparisons suggest that the most extreme cores form preferentially in brightest cluster galaxies at the centers of massive galaxy clusters, environments where multiple major mergers are most likely to occur. The implications of Holmberg 15A's core extend beyond understanding this single galaxy. The core serves as a fossil record of violent merger events in the early universe. By studying cores in detail, astronomers can reconstruct merger histories and test predictions from cosmological simulations about how structures form hierarchically. The existence of such massive cores also constrains theories of supermassive black hole growth. If cores form through binary black hole scouring, then detecting gravitational waves from these mergers should be possible with future space-based detectors like LISA, the Laser Interferometer Space Antenna. Holmberg 15A's core thus connects observations of present-day galaxy structure to future detections of gravitational wave signals, providing a complete picture of how the most massive black holes in the universe formed and merged over cosmic time. Brightest cluster galaxies. Why the biggest galaxies host the biggest black holes. Brightest cluster galaxies represent a special class of objects occupying a unique position in the cosmic hierarchy. As the name suggests, BCGs are the most luminous galaxies in their clusters, typically located at or very near the cluster center. They're almost always giant elliptical galaxies, with luminosities reaching trillions of solar luminosities, dwarfing normal galaxies like the Milky Way, which has a luminosity of roughly 20 to 30 billion solar luminosities. Holmberg 15A, as the brightest galaxy in Abell 85, exemplifies this class. BCGs form through a process called hierarchical assembly, where smaller galaxies merge together over cosmic time to build progressively larger systems. Galaxy clusters themselves form hierarchically, with smaller groups of galaxies merging to form larger clusters. The central region of a cluster is a special environment where mergers are frequent. Galaxies falling into the cluster center experience dynamical friction, a drag force arising from gravitational interactions with other galaxies and with the cluster's dark matter halo. Dynamical friction causes infalling galaxies to lose orbital energy and spiral toward the cluster center. When galaxies reach the center, they can merge with the BCG. Each merger adds stars to the BCG, increasing its mass and luminosity. Because the BCG sits at the bottom of the cluster's gravitational potential well, it's particularly efficient at capturing and consuming other galaxies. Over billions of years, a BCG can undergo dozens or even hundreds of mergers, growing to enormous mass. The largest BCGs, like Holmberg 15A, have masses exceeding 1 trillion solar masses, representing the accumulated stellar populations of many merged progenitors. The merger history is recorded in various observational signatures. Many BCGs show extended, faint outer envelopes, representing tidally stripped stars from disrupted satellites. Some show multiple nuclei or off-center bright knots, indicating recent mergers where the cores of satellite galaxies haven't yet fully merged with the BCG center. Holmberg 15A appears relatively smooth, suggesting its mergers occurred sufficiently long ago that tidal disruption and violent relaxation have smoothed out substructures. The connection between BCGs and massive black holes arises naturally from the merger-driven growth scenario. Each galaxy that merges with the BCG brings its own central supermassive black hole. These black holes, like the stars, sink toward the center through dynamical friction and eventually form a binary black hole system with the BCG's existing central black hole. The binary subsequently hardens through stellar and gas dynamical interactions and eventually merges, combining the masses of the two progenitor black holes into a single, more massive black hole. This process can repeat many times. If a BCG undergoes 10 major mergers, with galaxies each hosting billion solar mass black holes, the final merged black hole could have a mass of roughly 10 billion solar masses, assuming mass is roughly conserved during mergers. For Holmberg 15A's 40 billion solar mass black hole, the formation history likely involved mergers with galaxies hosting multi-billion solar mass black holes, possibly including one or two particularly massive progenitors with black holes already in the tens of billions range. Observational studies confirm that BCGs systematically host more massive black holes than galaxies of comparable stellar mass in less dense environments. This offset from the standard black hole mass-galaxy mass relationship indicates that BCGs have undergone additional black hole growth through mergers beyond what's experienced by field galaxies. The offset is particularly pronounced for the most massive BCGs, like Holmberg 15A, which lies significantly above scaling relations defined by smaller galaxies. The environment of galaxy clusters also affects black hole growth through gas accretion, though this mechanism is thought to be less important than mergers for the most massive black holes. Galaxy clusters contain vast reservoirs of hot gas in the intracluster medium, and in principle, this gas could cool and fall onto the central BCG, providing fuel for black hole accretion. However, observations show that most BCGs have very low accretion rates, with their black holes largely quiescent. Energetic feedback from past accretion episodes, possibly in the form of jets, likely heats the surrounding gas and prevents efficient cooling, self-regulating the accretion process. Holmberg 15A shows minimal signs of current accretion activity, fitting the pattern seen in many BCGs. X-ray observations reveal no strong nuclear source, indicating the black hole is not accreting significant amounts of gas currently. Radio observations detect very weak emission, possibly from a faint jet or from stellar processes, but nothing like the powerful radio sources seen in actively accreting systems. This quiescence is expected for a black hole in a hot gas-poor environment, and confirms that Holmberg 15A's black hole grew primarily through mergers rather than accretion. Large observational surveys have systematically studied BCGs across different cosmic epochs to understand their evolution. The Sloan Digital Sky Survey identified thousands of galaxy clusters and their BCGs, enabling statistical studies of BCG properties as functions of cluster mass, redshift, and environment. These surveys reveal that the most massive BCGs preferentially reside in the most massive clusters, as expected from hierarchical formation models. Additionally, BCGs at higher redshifts tend to be less massive and less luminous than their local counterparts, demonstrating that BCG growth continues over cosmic time. Deep surveys with instruments like the Hubble Space Telescope have traced BCG evolution back to when the universe was only a few billion years old, showing that even at early times, the most massive galaxies occupied cluster centers, though they were significantly less massive than present-day BCGs like Holmberg 15A. The timescales involved in BCG formation span billions of years, with most growth occurring relatively early in cosmic history. Simulations suggest that BCGs assemble roughly half their final mass by a redshift of 1, corresponding to when the universe was about half its current age. The growth rate subsequently slows as the supply of infalling galaxies diminishes and merger rates decline. For Holmberg 15A, its smooth morphology and large depleted core suggest that major mergers ceased at least several billion years ago, allowing time for the galaxy to relax into its current configuration. However, minor mergers with smaller satellite galaxies likely continue at a low rate, gradually adding mass through a process sometimes called cannibalism. Theoretical predictions for BCG evolution come from cosmological simulations that model structure formation from the early universe to the present day. These simulations incorporate dark matter dynamics, gas physics, star formation, and black hole growth and feedback. State-of-the-art simulations successfully reproduce many observed properties of BCGs, including their masses, sizes, and central black hole masses. However, producing the most extreme systems, like Holmberg 15, remains challenging. Some simulations underpredict the masses of the most massive black holes, suggesting either that merger rates in the densest environments are underestimated, or that additional physics, such as particularly efficient black hole feeding during mergers, needs to be incorporated. Future observations will refine our understanding of BCG and black hole coevolution. Next-generation telescopes, like the Extremely Large Telescope and the James Webb Space Telescope, will enable detailed studies of BCG structure and kinematics with unprecedented resolution, potentially revealing subtle features that constrain merger histories. Advances in gravitational wave astronomy may eventually detect the merger events that built systems like Holmberg 15A, providing direct confirmation of the merger-driven growth scenario and measuring black hole masses and spins independently of electromagnetic observations. TUN 618 versus Holmberg 15. A. The debate over which is truly largest. The question of which black hole is the absolute largest known is complicated by measurement uncertainties and by the different methods used for different objects. Holmberg 15A's black hole, measured at roughly 40 billion solar masses using stellar dynamics, competes for the title with TON 618, a distant quasar with a black hole mass estimated at 40 to 66 billion solar masses, using a completely different technique based on quasar emission properties. Understanding the strengths and limitations of each measurement helps appreciate the uncertainties in these extreme objects. TON 618 was identified in the 1970 seconds as an extremely luminous quasar, one of the brightest known, located at a redshift of 2.219, corresponding to a distance of about 10 billion light-years. Its name comes from the Tonnant-Zintler Observatory catalogue. The quasar's extreme luminosity, roughly equivalent to the light from 140 trillion suns, indicated the presence of an extraordinarily massive black hole-accreting gas at a prodigious rate. But how massive? Black hole mass estimates for quasars use reverberation mapping or single-epoch virial methods based on emission line properties. The basic principle is that the width of broad emission lines which originate from gas moving at high velocities in the black hole's gravitational field, depends on the black hole's mass. Faster orbital velocities, producing broader lines, indicate a more massive black hole. The size of the emission region, inferred from reverberation lags or from correlations with luminosity, combined with the velocity, allows estimating mass using the virial theorem. For TON 618, mass estimates published in 2004 and 2008 used the width of broad emission lines, particularly the MG2 line, combined with estimates of the emission region size based on quasar luminosity. These methods are calibrated against lower mass AGN, where reverberation mapping provides direct measurements, then extrapolated to high masses. The results for TON 618 yielded masses in the range of 40 to 66 billion solar masses, with typical quoted values around 66 billion. However, these quasar mass estimates have larger uncertainties than stellar dynamical measurements. The methods assume the gas in the broad line region is in virial equilibrium, meaning gravitational forces balance kinetic energy, which may not be strictly true if outflows or radiation pressure significantly affect the gas dynamics. The geometry of the emission region is uncertain and affects the conversion from measured line widths to masses. Different geometries, such as a thin disk versus a spherical distribution, give different masses for the same observed line width. Additionally, the calibration of the luminosity size relationship used to estimate emission region sizes has uncertainties and may not hold at the extreme luminosities of objects like TON 618. If the emission region is larger than assumed, the derived black hole mass decreases. If smaller, mass increases. Systematic uncertainties of factors of 2 to 3 are common for single epoch virial mass estimates, meaning TON 618's true mass could range from perhaps 20 billion to over 100 billion solar masses. In contrast, Holmberg 15A's measurement using stellar dynamics is based on resolved observations of stellar velocities, providing more direct constraints. The uncertainties, while still substantial at roughly 30 to 50 billion solar masses, arise primarily from modeling assumptions rather than systematic biases in the technique. Most astronomers consider stellar dynamical masses more reliable than quasar virial masses when both are available, though quasar methods are the only option for the most distant objects where stellar dynamics cannot be resolved. Another contender occasionally mentioned is IC 1101, a massive elliptical galaxy in the Abell 2029 cluster. Early estimates suggested IC 1101 might host a black hole of 40 to 100 billion solar masses, based on its large core and high central velocity dispersion. However, more recent analyses with better data and more sophisticated modeling have revised these estimates downward to roughly 10 to 50 billion solar masses, still enormous but likely not exceeding Holmberg 15A. Phoenix A, discussed in more detail in the next chapter, is another candidate. Recent X-ray observations of the powerful jets from Phoenix A's black hole suggest a mass that could rival or exceed Holmberg 15A's. However, mass estimates based on jet power are indirect and have large uncertainties. Until resolved stellar dynamical observations are obtained for Phoenix A, comparable to those for Holmberg 15A, its black hole mass will remain uncertain. The competition for the largest black hole title illustrates the challenges in measuring these extreme objects and the importance of multiple independent techniques. As instrumentation improves and more galaxies are studied in detail, the current record holders may be superseded. But regardless of which specific object holds the record, Holmberg 15A's black hole represents an important milestone, demonstrating that black holes can reach masses of at least 40 billion solar masses and providing a laboratory for studying black hole physics at the most extreme scales accessible to current observations. The historical evolution of black hole mass records reveals how dramatically our understanding has progressed. In the 1,990 seconds, the most massive confirmed black holes were only a few billion solar masses, with M87's black hole representing the upper extreme at roughly 6 billion solar masses. The discovery of increasingly massive black holes in the 2000s, including objects like OJ287, with an estimated 18 billion solar mass primary black hole in a binary system, pushed the boundaries significantly. TON 618's mass estimate, when published in the mid-2000s, represented a quantum leap to masses exceeding 60 billion solar masses, though with the substantial uncertainties discussed above. Holmberg 15A's measurement, announced in 2019, provided the first stellar dynamical confirmation that black holes of 40 billion solar masses or more actually exist, removing some of the uncertainty that surrounded quasar-based estimates. The methodology differences between TON 618 and Holmberg 15 and measurements extend beyond just the techniques themselves to the fundamental nature of what's being observed. TON 618 is caught in an active accretion phase, with vast amounts of gas spiraling into the black hole and generating enormous luminosity. This activity provides the emission lines needed for virial mass estimation, but also introduces complications. The intense radiation pressure from the accreting material can drive powerful outflows that contaminate the broad line region kinematics, potentially causing measured velocities to overestimate the true gravitational velocities and thus overestimate the black hole mass. Holmberg 15, conversely, shows minimal current accretion activity, meaning its measurement relies purely on the gravitational influence on surrounding stars without complications from active accretion physics. Theoretical considerations also enter the debate about maximum black hole masses. Some models of black hole growth suggest natural limits arising from feedback processes. As a black hole grows through accretion, the radiation it emits can heat and disperse the surrounding gas, cutting off the fuel supply and self-limiting growth. This Eddington limit mechanism suggests black holes should struggle to exceed certain mass thresholds through accretion alone. However, black hole mergers can bypass these limits by combining two already massive black holes without requiring sustained accretion. The fact that both TON 618 and Holmberg 15A appear to have masses approaching or exceeding 40 billion solar masses suggests either that Eddington limited growth can be sustained for extraordinarily long periods under optimal conditions, or, more likely, that major mergers play a crucial role in building the most massive black holes. The implications of these ultramassive black holes extend to fundamental questions about galaxy and black hole coevolution. Both TON 618 and Holmberg 15A exist in different contexts. TON 618 as a distant, actively growing system seen in the earlier universe, and Holmberg 15A as a nearby, quiescent system in the present-day universe. This suggests that different pathways or epochs may contribute to building ultramassive black holes. Understanding whether these objects represent the same evolutionary sequence, viewed at different stages, or fundamentally different formation channels, remains an active area of research that will require larger samples of ultramassive black holes with reliable mass measurements. Phoenix A, the other contender for the heavyweight title. Phoenix A, also known by its catalogue designation 2 Mass X J2, 3444387 to 4536431, is a massive elliptical galaxy located approximately 5.8 billion light-years from Earth at the center of the Phoenix Cluster, one of the most massive and luminous galaxy clusters known. The Phoenix Cluster, discovered in 2010 data from NASA's Wide Field Infrared Survey Explorer, or WISE, stands out for its extraordinary X-ray luminosity, indicating a very massive and hot intracluster medium. At its heart lies Phoenix A, and at Phoenix A's heart lurks a supermassive black hole that may rival Holmberg 15A's as the universe's most massive. The Phoenix Cluster's extreme properties made it an immediate target for follow-up studies. Observations with the Chandra X-ray Observatory revealed that the cluster's intracluster medium is cooling at a rate of several thousand solar masses per year, one of the highest cooling rates ever observed. This cooling gas should be falling onto Phoenix A, providing fuel for black hole accretion. And indeed, radio observations detect powerful jets emanating from Phoenix A, indicating the black hole is actively accreting and launching outflows. The jets from Phoenix A are among the most powerful known, pumping enormous amounts of energy into the surrounding medium. This energy output, measured through the mechanical work done by jets pushing against the ICM and inflating cavities, allows estimating the accretion rate onto the black hole. The relationship between jet power and accretion rate depends on the efficiency of converting accreted mass into jet energy, but typical efficiencies of a few percent to 10% are assumed based on theoretical models. Using the measured jet power of roughly 10 to the 46 ergs per second, astronomers estimate Phoenix A's black hole is accreting at a rate of tens to hundreds of solar masses per year. This accretion rate is extraordinarily high by the standards of local supermassive black holes, but is necessary to power the observed jets. The accretion likely proceeds through a geometrically thin, optically thick accretion disk, the standard model for efficiently accreting systems, with the disk emitting primarily at optical and ultraviolet wavelengths. The black hole mass can be estimated indirectly from the jets and accretion properties using scaling relations between black hole mass, jet power, and accretion rate. These relations are calibrated using samples of actively accreting black holes with known masses. Applying these relations to Phoenix suggests a black hole mass in the range of 20 to 100 billion solar masses, with central estimates around 50 to 60 billion solar masses. If correct, this would make Phoenix A's black hole comparable to, or possibly more massive than, Holmberg 15A's. However, these mass estimates have substantial uncertainties. The scaling relations used to infer mass from jet power are empirical, based on correlations observed in other systems, and may not hold precisely for objects at the extreme end of the distribution like Phoenix A. The accretion efficiency, determining how much mass must be accreted to produce a given jet power, is uncertain and could vary depending on black hole spin and magnetic field properties. Small changes in assumed efficiency translate to large changes in estimated mass. Direct measurements of Phoenix A's black hole mass using stellar dynamics, comparable to what was done for Holmberg 15A, have not yet been performed. Phoenix A's extreme distance of 5.8 billion light-years makes such observations very challenging, even with current facilities. The angular scale corresponding to Phoenix A's core, where stellar dynamical measurements would be most sensitive, is extremely small, requiring excellent spatial resolution that may only be achievable with next-generation extremely large telescopes or space-based facilities. Another approach to estimating Phoenix A's black hole mass uses the relationship between black hole mass and host galaxy properties. Phoenix A is an extremely massive galaxy with a high velocity dispersion, and correlations between black hole mass and velocity dispersion suggest a mass of several tens of billions of solar masses. However, these correlations have scatter, especially for the most massive systems, and Phoenix A may not follow the average relation given its extreme properties. The Phoenix cluster's environment also provides clues. As the central galaxy of such a massive and active cluster, Phoenix A has likely undergone numerous mergers throughout its history, similar to Holmberg 15A. Each merger would have added mass to the black hole through black hole mergers, potentially building it up to ultramassive scales. The cluster's high X-ray luminosity and cooling rate suggest that Phoenix A is currently in an unusually active phase, perhaps triggered by a recent major merger that both enhanced black hole accretion and disturbed the cluster's thermal structure. Comparing Phoenix A and Holmberg 15, A highlights the complementary nature of different black hole mass measurement techniques. Holmberg 15A's mass is measured precisely using stellar dynamics, but the black hole is largely quiescent, providing limited information about accretion processes. Phoenix A's mass is less well constrained, but the active accretion and jets provide insights into black hole fueling and feedback processes operating at extreme scales. Together, these objects bracket the range of behaviors possible for ultramassive black holes. Future observations will hopefully resolve the question of which black hole is truly more massive. For Phoenix A, spatially resolved spectroscopy with next-generation facilities could enable stellar dynamical modeling comparable to Holmberg 15A's. For both objects, continued monitoring and improved modeling techniques may reduce uncertainties in mass estimates, and surveys searching for additional ultramassive black holes may discover objects that surpass both current record holders, pushing the boundaries of what's possible for black hole growth. Binary black hole merger theory. Did two monsters become one? The binary black hole merger scenario for Holmberg 15A's black hole formation addresses a fundamental question. How do black holes grow to such extreme masses? A single black hole accreting gas steadily over billions of years could in principle reach tens of billions of solar masses, but this requires sustained accretion at high rates for cosmologically significant times. Observations suggest most supermassive black holes spend most of their time accreting slowly or not at all, making pure accretion growth difficult. Binary mergers provide an alternative path to ultramassive black holes. The scenario begins with Holmberg 15A's formation through galaxy mergers. As discussed earlier, BCGs form hierarchically through numerous mergers with smaller galaxies over cosmic time. Some of these mergers are minor, involving small satellite galaxies that contribute modest mass to the BCG. Others are major mergers with galaxies of comparable mass, which can profoundly reshape the BCG. Each merging galaxy brings its central supermassive black hole, typically with masses from millions to billions of solar masses, depending on the galaxy's size. When two galaxies merge, their black holes initially remain separated by distances comparable to the galactic sizes, thousands to tens of thousands of light years. Dynamical friction acts on each black hole, causing it to spiral toward the center of the merged galaxy. The timescale for this spiral depends on the black hole mass and the density of stars and dark matter it's moving through. For massive black holes in dense central regions, dynamical friction is efficient, and in spiral occurs over tens to hundreds of millions of years. Once both black holes reach the central kiloparsec or so, they form a gravitationally bound binary. At this stage, they're orbiting their common center of mass with an orbital period perhaps measured in millions of years initially. the binary continues to shrink through interactions with stars passing nearby. When a star approaches the binary closely enough, gravitational interactions deflect the star's trajectory, transferring energy from the binary to the star. The binary loses energy and orbital angular momentum, causing the two black holes to move closer together. This hardening process is relatively efficient initially, when many stars pass through the binary's sphere of influence. But as the binary shrinks, fewer stars have orbits, bringing them close enough for efficient interaction. The binary can become stalled at separations of a parsec or so, a phenomenon called the final parsec problem. Overcoming this problem requires either a continuous supply of stars on appropriate orbits, which may occur in triaxial galaxy potentials, or the presence of gas that can extract energy from the binary through torques. For Holmberg 15a, the large core provides evidence that binary hardening did proceed efficiently past the final parsec, eventually leading to merger. Simulations show that a binary black hole scatters stars primarily from the central region, creating the core deficit discussed earlier. The size of the core is related to the binary's properties, with larger cores indicating more massive binaries that survived longer before merging. Holmberg 15a's 15,000 light-year core suggests a binary with combined mass of several tens of billions of solar masses that existed for tens to hundreds of millions of years. When the binary shrinks to separations of roughly 0.01 parsecs or smaller, gravitational wave emission becomes the dominant mechanism for further shrinkage. Gravitational waves carry away energy and angular momentum, causing the binary's orbit to decay. The gravitational wave luminosity scales strongly with black hole masses and with orbital frequency, becoming enormous as the binary approaches merger. In the final seconds before merger, the system radiates more energy in gravitational waves than all the stars in the observable universe combined emit in electromagnetic radiation. The merger itself is a violent event. The two event horizons touch and rapidly coalesce into a single, highly distorted black hole. This distorted hole oscillates, ringing like a struck bell, emitting gravitational waves at characteristic frequencies determined by the final mass and spin. These ring-down gravitational waves damp over timescales of milliseconds to seconds, leaving a stationary black hole with mass slightly less than the sum of the progenitor masses, the deficit having been radiated as gravitational waves. For Holmberg 15a's black hole, if it formed through a major merger of two progenitor black holes, each progenitor would have had a mass of roughly 20 billion solar masses, or there was one more massive progenitor paired with a smaller one. The gravitational waves from such a merger would have had frequencies in the nanohertz to microhertz range, far too low for current ground-based detectors like LIGO, but potentially detectable by future space-based detectors or by pulsar timing arrays. Pulsar timing arrays search for gravitational waves by precisely timing the arrival of radio pulses from multiple pulsars distributed across the sky. Gravitational waves passing between Earth and a pulsar stretch and compress space-time, causing correlated timing variations. The Nanograv, European Pulsar Timing Array, and International Pulsar Timing Array collaborations have been collecting data for over a decade, and in 2023 announced evidence for a gravitational wave background consistent with supermassive black hole binaries. Some of this signal may come from binaries, like the one that formed Holmberg 15a's black hole, though individual events cannot yet be resolved. Core scouring: how merging black holes eject billions of stars. Core scouring is a gravitational dynamical process where a binary black hole system ejects or scatters stars from a galaxy's central region, creating the depleted cores observed in massive ellipticals like Holmberg 15a. Understanding this process in detail requires combining insights from orbital mechanics, stellar dynamics, and N-body simulations that track the interactions of millions of particles representing stars. The process leaves observational signatures that allow reconstructing the merger history of galaxies hosting ultramassive black holes. The basic mechanism involves three-body gravitational interactions. When a star passes near a binary black hole, the star experiences gravitational forces from both black holes. If the star passes close enough, these forces can significantly change the star's velocity and trajectory. In most encounters, the star gains energy at the expense of the binary's orbital energy, causing the binary to shrink while the star is scattered to a higher orbit or ejected from the galaxy entirely. The efficiency of this process depends on the binary's properties and on the stellar distribution. Harder binaries, meaning those with larger binding energies, scatter stars more efficiently. For a binary with black holes of masses m1 and m2, separated by distance a, the binding energy is proportional to g times m1 times m2a. As the binary hardens and decreases, the binding energy increases, and each interaction ejects stars more violently. The binary extracts energy from passing stars, maintaining or even increasing its binding energy despite shrinking. The rate at which stars interact with the binary depends on the stellar density near the binary and on the cross-section for interactions. The loss cone describes stars on orbits that will pass close enough to the binary for significant interactions. Stars enter the loss cone through various processes, including two-body relaxation, where gravitational encounters between stars randomly change their orbits, and through scattering by the binary itself, which can send stars away on trajectories that will eventually return for another interaction. N-body simulations track these processes by following the gravitational interactions of millions of particles. Each particle represents a stellar mass, and the simulation computes gravitational forces between all pairs of particles, updating their positions and velocities at each time step. Running such simulations for binary black holes in galaxy models requires enormous computational resources, but modern supercomputers have enabled simulations realistic enough to reproduce observed cores. The results show that a binary black hole can eject or scatter roughly its own mass in stars from the central region. For Holmberg 15A's 40 billion solar mass black hole formed from a binary, this means roughly 40 billion solar masses of stars could be removed from the core. Given that the observed mass deficit is several billion solar masses, somewhat less than the black hole mass, this is consistent with theoretical expectations, especially considering that some scattered stars remain bound and don't fully escape the core. The spatial distribution of ejected stars provides additional information. Most stars are ejected at relatively low velocities, remaining bound to the galaxy but scattered to larger radii. These stars contribute to the galaxy's outer envelope, potentially creating extended low-surface brightness components. A fraction of stars are ejected at velocities exceeding the galaxy's escape velocity, becoming intergalactic stars. Simulations predict that core scouring could populate the intracluster medium with a population of such stars stripped from galaxies during mergers. The timescale for core scouring depends on the stellar density and the binary hardening rate. Typical timescales are tens to hundreds of millions of years, meaning core formation is not instantaneous but proceeds gradually as the binary evolves. During this time, the core grows larger as the binary hardens and scatters stars from progressively larger radii. The final core size is reached when the binary merges or when the stellar density becomes too low to support efficient further scattering. Observations of cores in massive ellipticals support the core scouring scenario. As mentioned, there's a correlation between core size and galaxy mass, consistent with more massive galaxies hosting more massive binaries that create larger cores. There's also evidence for departures from perfect power law profiles in core regions, with some cores showing plateaus or even slight central cusps, possibly indicating partial refilling through later star formation or stellar evolutionary processes. The kinematics within cores also bear the imprint of core scouring. Simulations predict that scattering preferentially affects stars on certain orbits, creating anisotropies in the velocity distribution. Specifically, stars on circular or near-circular orbits are more easily scattered because they spend more time near the binary, while stars on radial orbits that plunge quickly through the central region have fewer interactions. This produces a radially anisotropic velocity distribution where stars preferentially move on elongated radial orbits. Observations of Holmberg 15A's central kinematics show evidence for such anisotropy, though the signal is not yet measured precisely enough to provide tight constraints. Future observations with better spatial resolution and signal-to-noise could confirm this prediction and provide a more detailed test of core scouring models. Combining kinematic observations with dynamical modelling that includes the effects of core scouring would allow reconstructing the binary's properties and merger history in more detail. 700 million light-years from Earth, the journey of light we see today. Understanding that Holmberg 15A lies 700 million light-years away means the light we observe today left the galaxy 700 million years ago, when the universe was about 5% younger than it is today. This light has travelled across expanding space, carrying information about conditions in Holmberg 15A at that earlier epoch. By the time photons from Holmberg 15A reach Earth, they've journeyed across a universe containing billions of galaxies, through intergalactic space filled with diffuse gas and dark matter, and finally through our own Milky Way and Earth's atmosphere. The distance of 700 million light-years is determined through the cosmological redshift of Holmberg 15A's spectrum. Redshift measures how much spectral lines are shifted toward longer, redder wavelengths due to the expansion of space. For Holmberg 15A, the redshift is approximately Z equals 0.055, meaning wavelengths are stretched by a factor of 1. 0.55 compared to their rest values. This redshift corresponds to a light travel time of about 700 million years in the standard cosmological model, with Hubble constant 70 km per second per megaparsec and matter density parameter 0.3. The redshift also affects the observed properties of Holmberg 15A. The galaxy's light is dimmed by the expansion of space through two effects. The increase in wavelength reduces each photon's energy, and the expansion decreases the rate at which photons arrive. Combined, these effects reduce the observed brightness by a factor of approximately 1 plus Z, 4, or about 1.24 for Holmberg 15A. Astronomers correct for this dimming when measuring the galaxy's intrinsic luminosity. During the 700 million year journey, the photons encountered essentially nothing. Intergalactic space is remarkably empty, with average densities of about 1 hydrogen atom per cubic meter. At this density, a photon travels for years between interactions with atoms. The probability of a photon being absorbed or scattered during its journey from Holmberg 15A to Earth is negligible, which is why we can observe distant galaxies at all. If intergalactic space were opaque, we'd only see nearby objects. However, the photons did experience some interactions. As they passed through regions of ionized hydrogen in the intergalactic medium, free electrons scattered some of the light through a process called Compton scattering. This scattering is weak but detectable statistically in surveys of many galaxies. The cumulative effect of scattering along 700 million light-years produces a slight blurring and redistribution of light, though for practical purposes this is negligible for an individual galaxy like Holmberg 15a. The expanding universe during the photon's journey also affected their properties. When the photons left Holmberg 15a, the universe was 5% smaller than today, meaning distances between galaxies were correspondingly smaller. As space expanded, carrying the photons with it, wavelengths stretched continuously. This stretching wasn't a sudden jump, but a gradual process occurring throughout the journey. The expansion rate itself has changed during this time, having been slightly faster 700 million years ago when the universe was younger and matter density was higher. The cosmic microwave background, the relic radiation from the Big Bang, provided a reference frame during the journey. This radiation fills all of space with a nearly uniform temperature of 2.7 Kelvin today. When photons from Holmberg 15a were emitted, the CMB temperature was about 2.85 Kelvin, slightly warmer due to the universe being smaller and denser. The photons from Holmberg 15a travelled through this CMB radiation C, occasionally interacting with CMB photons through photon-photon scattering, though such interactions are extremely rare. Upon reaching the Milky Way, the photons passed through our galaxy's halo, disk, and finally Earth's atmosphere. The halo is essentially transparent at optical wavelengths, contributing negligible absorption or scattering. The disk contains dust that can absorb and scatter light, particularly toward the galactic plane. But Holmberg 15a lies at high galactic latitude where dust extinction is minimal, perhaps 0.1 magnitudes or less. Earth's atmosphere is the final and most variable barrier, with clouds, water vapor, and turbulence all affecting the light before it reaches a telescope. The fact that we can observe Holmberg 15a at all, detecting individual spectral lines and measuring velocity dispersions, is remarkable given the distance. Each square meter of Earth's surface receives only about 10 million photons per second from Holmberg 15a, integrated across all wavelengths. A telescope with an area of 50 square meters, typical for major observatories, collects about 500 million photons per second. But only a tiny fraction, perhaps 1 in a million, are at wavelengths corresponding to specific absorption lines needed for velocity dispersion measurements. This is why observations require hours of exposure time to accumulate sufficient photons. The Gemini Observatory observations that mapped the core. The Gemini Observatory, the facility that provided the critical data for measuring Holmberg 15a's black hole mass, represents one of the premier ground-based astronomical facilities in the world. The observatory consists of two 8.1-meter telescopes, Gemini North on Mauna Kea in Hawaii and Gemini South on Cerro Pachon in Chile. Together, they provide full sky coverage, with Gemini North observing the northern sky and Gemini South the southern sky. For Holmberg 15a, located at declination -9 degrees in the constellation Cetus, either telescope could observe it, but Gemini North was used for the key observations. The Gemini telescopes were designed and built in the 1990 seconds as part of an international partnership including the United States, United Kingdom, Canada, Chile, Australia, Brazil, and Argentina. Each telescope features an alt-azimuth mount, meaning it can point in altitude and azimuth coordinates, and active optics that continuously adjust the primary mirror shape to compensate for gravity and temperature effects. The 8.1 meter primary mirror is relatively thin, only 20 centimeters thick, and requires active support to maintain its optimal figure. For the Holmberg 15A observations, the Gemini Multi-Object Spectrograph, or GMOS, was the instrument of choice. GMOS is an optical spectrograph that can observe multiple objects simultaneously using a slit mask, or observe extended objects like galaxies using a long slit. The instrument covers wavelengths from about 4,000 to 10,000 angstroms, spanning the visible spectrum from blue to near infrared. Spectral resolution can be adjusted by changing gratings, with typical resolving powers of 2,000 to 5,000, adequate for measuring velocity dispersions of a few hundred kilometers per second. The observations were conducted in long slit mode, where a single narrow slit, typically 0.5 to 1 arcseconds wide, is placed across the galaxy center. Light from the galaxy passing through the slit is dispersed by a grating, creating a spectrum. Because the slit is extended, covering multiple positions along the galaxy, the resulting data is a two-dimensional image showing wavelength in one direction and position along the slit in the other direction. This allows measuring how spectral features change with position, revealing kinematics as a function of location in the galaxy. The slit was oriented to pass through Holmberg 15A's nucleus along the galaxy's major axis, the direction of maximum extent. Multiple exposures were taken with total integration time of several hours to achieve the required signal-to-noise ratio. The observations were scheduled for nights with excellent seeing conditions, meaning minimal atmospheric turbulence, to achieve spatial resolution approaching the 0.2 arcsecond goal. Seeing is quantified by the full width at half maximum of stellar images, with good seeing at Mauna Kea being 0.4 to 0.6 arcseconds, and excellent seeing being better than 0.4 arcseconds. The raw data from GMOS underwent extensive processing. First, standard calibration steps removed instrumental signatures, including bias levels, dark current, and pixel-to-pixel sensitivity variations. Flat field images, taken by observing uniformly illuminated screens, corrected for variations in detector response. Wavelength calibration used arc lamp spectra with known emission lines to establish the wavelength scale precisely. Sky subtraction removed the bright background from Earth's atmosphere, which emits faint light from oxygen and other species. After calibration, the two-dimensional spectrum was extracted into one-dimensional spectra for each position along the slit. Each spectrum showed absorption lines from stars in Holmberg 15A at that position. The spectra were then analyzed to measure velocity dispersion. This involved fitting the observed spectra with templates constructed from models of stellar populations with known properties. The template is convolved with a Gaussian representing the velocity distribution, and the width of this Gaussian, giving the best fit, is the velocity dispersion. The analysis revealed velocity dispersions exceeding 350 km per second in the central few arcseconds, declining to 250 to 300 km per second at larger radii. The spatial resolution was sufficient to resolve the central kiloparsec, though individual stellar orbits were far from resolved. The velocity dispersion profile, combined with surface brightness measurements from imaging data, provided the inputs for the dynamical modelling that determined black hole mass. The Gemini observations represented a substantial investment of telescope time, reflecting the scientific importance of characterizing such an extreme object. Telescope time on 8-meter class facilities is highly competitive, with typical oversubscription rates of 3 to 5 times, meaning only 1 in 3 to 5 proposals is awarded time. The Holmberg 15, a program, was judged sufficiently compelling to warrant the required time allocation, and the results justified this investment by delivering the first robust measurement of an ultramassive black hole's properties. X-ray silence. Why this giant barely glows in high energy. One of the most puzzling aspects of Holmberg 15A's central black hole is its relative faintness in X-rays. For a black hole with 40 billion solar masses, we might expect strong X-ray emission if it were actively accreting gas. Accreting black holes heat gas to millions of degrees in the inner accretion disk, and this hot gas emits copious X-rays. Yet observations with X-ray telescopes like Chandra and XMM Newton show that Holmberg 15A's nucleus is faint in X-rays, orders of magnitude dimmer than expected for efficient accretion. This X-ray silence tells us important things about how ultramassive black holes interact with their environments. The X-ray luminosity of an accreting black hole depends on the accretion rate and the efficiency with which gravitational potential energy is converted to radiation. For a black hole accreting at the Eddington limit, the maximum rate at which radiation pressure doesn't blow away infalling material, the X-ray luminosity is approximately 10 to the 38 times m/sun ergs per second, where m is the black hole mass. For Holmberg 15A's 40 billion solar mass black hole, Eddington luminosity would be about 4x10 to the 47 ergs per second, equivalent to roughly 10 trillion times the Sun's total luminosity. Observations show the actual X-ray luminosity is only about 10 to the 42 ergs per second, roughly 100,000 times lower than Eddington. This low luminosity indicates the accretion rate is far below the Eddington rate, perhaps only 0.001% or less of the maximum possible rate. The black hole is essentially starving, accreting little gas despite its enormous gravitational pull. Why? The answer lies in the environment surrounding the black hole. Holmberg 15A sits at the center of the Abell 85 cluster, embedded in the cluster's hot intra-cluster medium. This gas is already hot, roughly 10 to 50 million degrees Kelvin, and is not dense by ISM standards, with densities of perhaps 0.001 to 0.01 particles per cubic centimeter. For gas to accrete onto the black hole, it must cool radiatively and lose angular momentum, processes that are inefficient in this environment. Radiative cooling time depends on density and temperature. Lower density means fewer collisions between particles and slower cooling. Higher temperature means particles have more thermal energy to radiate away. For gas at 10 to 50 million Kelvin with densities of 0.001 to 0.01 particles per cubic centimeter, cooling times are billions of years, comparable to or exceeding the age of the universe. The gas simply doesn't cool fast enough to fall onto the black hole in significant amounts. Even if gas did cool, it would need to lose angular momentum to accrete. Gas in the cluster has angular momentum from the cluster's rotation and from turbulent motions. This angular momentum prevents gas from falling straight into the black hole. Instead, the gas settles into orbits, forming a hot atmosphere around the black hole. Losing angular momentum requires viscosity in the gas or magnetic torques, processes that operate slowly in the diffuse, hot environment. AGN feedback also plays a role. Although Holmberg 15A's black hole is currently accreting at a low rate, it may have accreted more vigorously in the past. Past accretion would have produced jets that pumped energy into the surrounding gas, heating it and preventing cooling. This creates a self-regulating feedback loop. Accretion generates energy that heats gas, reducing future accretion. The system settles into a quasi-equilibrium where low-level accretion provides just enough energy to balance radiative cooling, maintaining the gas at high temperature. Evidence for past AGN activity in Holmberg 15A includes the large core, which, as discussed earlier, likely formed through binary black hole core scouring. The binary phase presumably involved enhanced accretion as gas was funneled toward the black holes. Jets from this accretion could have inflated cavities in the intracluster medium, which might be detectable as depressions in X-ray surface brightness. However, detailed X-ray maps of Able 85 have not revealed obvious cavities associated with Holmberg 15, suggesting that any past activity has faded and the cavities have been filled in or were never prominent. Radio observations provide additional constraints on accretion and jet activity. Holmberg 15A is detected as a faint radio source, with luminosity about 10 to the 38 ergs per second at 1.4 GHz, characteristic of low luminosity AGN. This radio emission could come from a weak jet or from synchrotron emission from electrons in the galaxy. The radio to X-ray luminosity ratio is consistent with radiatively inefficient accretion flows. Theoretical models, where accretion occurs at rates far below Eddington and most of the released energy is carried across the event horizon rather than radiated. Comparing Holmberg 15A to actively accreting supermassive black holes highlights the dramatic range in accretion states. Quasars, where black holes accrete at substantial fractions of Eddington, can be billions of times more luminous than the galaxy hosting them. Holmberg 15A's black hole, despite being 10,000 times more massive than a typical quasar black hole, is millions of times less luminous, illustrating that mass and luminosity are only loosely related for supermassive black holes. Accretion rate, not mass, determines luminosity. Accretion rate mysteries. The starving supergiant paradox. The low accretion rate onto Holmberg 15A's black hole presents a theoretical puzzle when considered in the context of galaxy evolution and black hole growth models. How did such a massive black hole form if it currently accretes very slowly? If Holmberg 15A's black hole has accreted at its current low rate throughout cosmic history, it would have accumulated only a tiny fraction of its current mass. The bulk of the mass must have been acquired during earlier epochs, when accretion rates were much higher, or through mergers with other black holes, or both. Standard models of supermassive black hole growth invoke two main channels: gas accretion and black hole mergers. Gas accretion dominates for lower mass black holes, particularly during the quasar epoch at redshifts Z equals 2 to 3, roughly 10 to 11 billion years ago, when gas fractions in galaxies were higher and accretion rates onto black holes were correspondingly elevated. Many supermassive black holes reached masses of billions of solar masses during this epoch through sustained accretion at rates approaching the Eddington limit. But reaching tens of billions of solar masses through accretion alone is difficult. Even if a black hole accretes at the Eddington limit continuously, its mass grows exponentially with an E-folding time. The time to increase mass by a factor of E of about 45 million years, starting from a seed black hole of 100 solar masses at redshift Z equals 20, which is optimistic, and accreting continuously at Eddington. The black hole could reach a mass of roughly 10 billion solar masses by redshift Z equals 0.055, Holmberg 15A's redshift. Reaching 40 billion solar masses would require starting from a more massive seed or sustaining super Eddington accretion for extended periods. Super Eddington accretion, where radiation pressure doesn't limit infall, is possible if the accretion flow geometry is favorable. In some configurations, radiation escapes primarily along the polar directions, while accretion proceeds through the equatorial plane, allowing accretion rates exceeding Eddington. But sustaining super Eddington accretion for billions of years is challenging because the high luminosities generated would heat and ionize surrounding gas, suppressing further infall. Black hole mergers provide an alternative or complementary growth channel. As discussed earlier, Holmberg 15A's formation through galaxy mergers brought together multiple supermassive black holes that subsequently merged. If Holmberg 15A underwent, say, 5 major mergers, with galaxies each hosting 5 billion solar mass black holes, the mergers alone would build a 5 billion solar mass black hole. Combined with accretion adding another 15 billion solar masses, this could explain the current 40 billion solar mass black hole. The relative contributions of accretion and mergers to black hole growth can in principle be constrained through several observables. The black hole spin, measurable through X-ray spectroscopy of accreting systems, provides information about growth history. Prolonged accretion from a disk spins the black hole up toward maximum spin, while multiple random orientation mergers produce black holes with lower spins. Unfortunately, Holmberg 15A's low accretion rate makes spin measurements unfeasible with current techniques. Another constraint comes from the black hole mass to bulge mass ratio. Observations of large galaxy samples show a correlation between black hole mass and bulge stellar mass, with black holes typically containing about 0.1 to 0.5% of the bulge mass. Holmberg 15A's black hole mass of 40 billion solar masses and bulge mass of roughly 10 to 20 trillion solar masses give a ratio of about 0.2 to 0.4%, consistent with the correlation. This suggests Holmberg 15A's black hole growth tracked its host galaxy's growth through mergers. The timing of mass acquisition is also relevant. Did Holmberg 15A's black hole acquire most of its mass early, during the quasar epoch, or did it grow more gradually over cosmic time through a series of mergers? Observations of high redshift quasars show that billion solar mass black holes existed when the universe was less than 1 billion years old, demonstrating rapid early growth. But whether black holes as massive as 40 billion solar masses existed at high redshift is unknown, because such objects would be extremely rare and difficult to detect. The current low accretion rate onto Holmberg 15A's black hole likely represents a temporary state that will change when the next galaxy merger brings fresh gas into the central region. Mergers can funnel gas toward the galactic center through gravitational torques, overcoming the angular momentum barrier that normally prevents accretion. This could trigger an AGN phase, where the black hole accretes at much higher rates, shining as a luminous AGN or quasar. Such episodes may be intermittent, occurring every few 100 million years when mergers deliver gas, with long quiescent intervals in between. Gravitational waves from the past, evidence hidden in space-time, ripples. If Holmberg 15A's ultramassive black hole formed through a major merger of 2 progenitor black holes, the merger would have produced gravitational waves of enormous amplitude. These waves, ripples in the fabric of space-time itself, carry energy away from the binary system and propagate at the speed of light. For a merger producing a 40 billion solar mass final black hole, the peak gravitational wave luminosity during the final moments would have exceeded 10 to the 57 ergs per second, outshining the entire electromagnetic output of all stars in the observable universe combined. Yet detecting these waves is extraordinarily challenging. Gravitational waves from supermassive black hole mergers have frequencies determined by the orbital frequency of the binary before merger. For black holes with masses in the billions to tens of billions of solar masses, orbital frequencies are very low, in the nanohertz to microhertz range. This corresponds to periods of years to months, far longer than the millisecond periods characteristic of stellar mass black hole mergers detected by LIGO. The low frequencies require completely different detection methods. Pulsar timing arrays represent the most developed technique for detecting gravitational waves in the nanohertz frequency range, relevant for supermassive black hole binaries. Pulsars are rapidly rotating neutron stars that emit beams of radio waves, and some pulsars are exceptionally stable clocks, with rotation periods stable to better than 1 part in 10 to the 15. By timing the arrival of pulses from many pulsars distributed across the sky over many years, astronomers can search for correlated timing variations that would indicate passing gravitational waves. Gravitational waves affect pulsar timing in a specific way. A wave passing between Earth and a pulsar alternately stretches and compresses spacetime, changing the distance the radio waves travel and thus the arrival times of pulses. The effect is tiny, measured in nanoseconds or less per pulse, but accumulates over thousands of pulses. Multiple pulsars observed simultaneously show correlated timing variations with a pattern called the Hellings-Downs curve, a mathematical prediction from general relativity for how correlations depend on the angular separation between pulsar pairs. Several international collaborations, including the North American Nanohertz Observatory for Gravitational Waves, or NanoGrav, the European Pulsar Timing Array, and the Parkes Pulsar Timing Array, have been timing pulsars for over a decade specifically to detect gravitational waves. In 2023, these collaborations announced evidence for a gravitational wave background, a stochastic signal from many unresolved supermassive black hole binaries throughout the universe. The signal has the statistical properties expected from a population of merging binaries, though individual events cannot yet be distinguished. Could gravitational waves from Holmberg 15A's black hole merger be contributing to this background? Almost certainly yes, though not as a detectable individual event. If the merger occurred 700 million years ago or earlier, the gravitational waves have been traveling through space for that long and have been redshifted by cosmic expansion. The original frequencies in the nanohertz to microhertz range have been shifted to lower frequencies. Additionally, the amplitude has been diluted by geometric spreading as the waves expanded across hundreds of millions of light-years. Even for a nearby merger, detecting a single event with current pulsar timing arrays is extremely challenging. Arrays would need to observe for decades with excellent timing precision on dozens of pulsars to detect an individual binary at distances of tens to hundreds of megaparsecs. Holmberg 15A, at 700 million light-years, is well beyond current detection limits for individual events. Future improvements in pulsar timing, precision, and array sensitivity, along with the discovery of additional stable millisecond pulsars, may eventually enable detection of individual nearby binaries. Space-based gravitational wave detectors represent another approach. The Laser Interferometer Space Antenna, or LISA, planned for launch in the 2030 seconds, will consist of 3 spacecraft in a triangular formation, with each spacecraft 2.5 million kilometers from its neighbors. Laser beams between spacecraft will measure distance changes induced by passing gravitational waves. LISA will be sensitive to frequencies from 0.1 MHz to 0.1 Hz, bridging the gap between pulsar timing arrays and ground-based detectors like LIGO. LISA's frequency range is too high to detect the inspiral of supermassive black holes as massive as Holmberg 15A's progenitors, which would emit primarily below 0.1 MHz. But LISA will detect intermediate mass black hole binaries with masses from thousands to millions of solar masses, providing insights into how black holes grow across cosmic time. LISA observations will complement pulsar timing array observations, together covering a wide range of black hole masses and formation scenarios. Gravitational wave observations have the potential to revolutionize our understanding of black hole populations and evolution. Unlike electromagnetic observations, which require black holes to be accreting to be detected, gravitational wave observations can detect any merging pair regardless of accretion state. This removes observational bias and provides access to the full population of black holes, including those in quiescent galaxies like Holmberg 15A. Multi-messenger observations combining gravitational waves with electromagnetic and neutrino observations will provide the most complete picture of these extreme cosmic events. The event horizon, a boundary larger than our entire solar system. The event horizon of Holmberg 15A's black hole defines the point of no return, the boundary beyond which nothing, not even light, can escape. For a non-rotating black hole, the event horizon radius is given by the Schwarzschild radius. Rs equals 2gm divided by c2, where g is the gravitational constant, m is the black hole mass, and c is the speed of light. For Holmberg 15A's 40 billion solar mass black hole, this works out to approximately 120 billion kilometers, or about 800 astronomical units. To put this in perspective, Neptune orbits the Sun at 30 AU, meaning Holmberg 15A's event horizon is roughly 27 times wider than Neptune's orbit. If you could place this black hole at the center of our solar system, its event horizon would extend far beyond the orbits of all planets. Even the Voyager spacecraft, currently in interstellar space, more than 150 AU from the Sun, would still be inside the event horizon. The Oort cloud, the distant reservoir of comets extending up to 100,000 AU from the Sun, would dwarf even this enormous event horizon, but the comparison illustrates the black hole's truly immense size. The event horizon is not a physical surface, but a mathematical boundary in spacetime. There's no material barrier at the horizon. An observer freely falling across it would experience nothing special at the moment of crossing. But once inside, all future trajectories lead inevitably to the singularity at the center. Light emitted inward crosses the horizon and never escapes. Light emitted exactly at the horizon remains there, hovering at the boundary. Only light emitted from outside the horizon can escape to reach distant observers. From far away, the event horizon appears as a dark circle, the shadow of the black hole. The Event Horizon Telescope, which famously imaged the supermassive black hole in M87 in 2019, resolved M87's event horizon shadow because the black hole is relatively close, at 55 million light-years, and has an event horizon roughly 5 times larger than its Schwarzschild radius due to its rapid spin. Holmberg 15A, at 700 million light-years distance, subtends a much smaller angle on the sky, despite its larger physical size. Calculating the angular size of Holmberg 15A's event horizon requires accounting for cosmological effects. The physical diameter is 1,600 AU, or about 2.4x 10 to the 14 kilometers. At a distance of 700 million light-years, or 6.6x 10 to the 24 kilometers, the angular size is approximately 0.04 micro-arc seconds. This is far too small to resolve with current technology. The Event Horizon Telescope achieves resolution of about 20 micro-arc seconds, more than 500 times larger than needed. Future improvements would require baseline lengths exceeding Earth's diameter, necessitating space-based interferometry. Inside the event horizon, space-time is dramatically warped. The radial direction becomes time-like, meaning that moving inward is as inevitable as moving forward in time. An observer inside cannot stop falling toward the singularity any more than we can stop moving into the future. The tidal forces grow stronger as the singularity approaches, stretching objects along the radial direction and compressing them perpendicular to it in a process called spaghettification. For a black hole as massive as Holmberg 15A's, tidal forces at the event horizon are relatively weak. An astronaut falling through the horizon would experience tidal accelerations of only a few micro-g, imperceptible to human senses. The astronaut would notice nothing special upon crossing, though they would already be doomed. This contrasts with stellar mass black holes, where tidal forces at the horizon are enormous and would tear apart any material object before it crosses. The journey from horizon to singularity takes a finite amount of proper time as measured by the infalling observer. For a non-rotating black hole, this time is approximately p, 2 times RSC, which for Holmberg 15A works out to about 6 hours. An astronaut falling through the horizon would reach the singularity 6 hours later by their clock. During this time, they could in principle send messages to other observers also inside the horizon and farther from the singularity. Though communication with the outside universe would be impossible, general relativity predicts that the singularity is a point of infinite density and curvature where the laws of physics break down. However, most physicists believe that quantum effects become important before densities become truly infinite, and that a full theory of quantum gravity is needed to describe what actually exists at the center. Various proposals suggest the singularity might be replaced by a region of extreme but finite density, a Planck star, or even a connection to another region of spacetime. Without a theory of quantum gravity, these ideas remain speculative. Spaghettification radius, where tidal forces tear stars apart. While tidal forces at Holmberg 15A's event horizon are weak, they become significant at smaller radii closer to the singularity. But for stars orbiting outside the black hole, tidal forces can be lethal at much larger distances. The tidal disruption radius, where tidal forces exceed a star's self-gravity and tear it apart, depends on both the black hole mass and the star's properties. For solar-type stars orbiting Holmberg 15A's black hole, the tidal disruption radius is well inside the event horizon, meaning stars can orbit safely even quite close to the black hole. Tidal forces arise because different parts of an extended object experience different gravitational forces. For a star orbiting a black hole, the side facing the black hole feels stronger gravity than the far side. This differential force stretches the star along the line connecting it to the black hole. Similarly, points on the star's surface perpendicular to this line feel gravity pulling them inward toward the line, compressing the star laterally. These tidal forces are the same mechanism that creates ocean tides on Earth from the Moon's gravity, just far stronger. The strength of tidal forces scales as F gm times r d3, where m is the black hole mass, r is the star's radius, and d is the distance from the black hole. Tidal forces increase rapidly as distance decreases, varying as the inverse cube of distance. They also increase linearly with black hole mass and star size. For a star to survive, its self-gravity must exceed the tidal forces trying to tear it apart. Self-gravity scales as Fgm2r2, where m is the star's mass. Setting tidal force equal to self-gravity and solving for the critical distance gives the tidal disruption radius, RT, r times m, m 1/3. For a solar mass, solar radius star orbiting Holmberg 15A's 40 billion solar mass black hole, this works out to roughly 1.5 astronomical units. This is inside the event horizon at 800 AU, meaning that the star would be swallowed whole before being tidally disrupted. The star would cross the horizon intact and only be torn apart well inside, where information about its disruption cannot escape. This result is counterintuitive. More massive black holes are gentler on stars at their event horizons. For a stellar mass black hole of 10 solar masses, the tidal disruption radius is about 100 times the Schwarzschild radius, meaning stars are shredded well outside the horizon. For intermediate mass black holes of 1,000 to 100,000 solar masses, tidal disruption occurs just outside or at the horizon. For supermassive black holes above about 100 million solar masses, tidal disruption occurs inside the horizon. Holmberg 15A's black hole, at 40 billion solar masses, is well into this regime. However, tidal disruption events can still occur for Holmberg 15A if stars on highly eccentric orbits approach very close before swinging back out. For a star on a parabolic orbit, essentially falling from infinity, the closest approach distance, called the periapsis, could be anywhere. If periapsis is at the tidal radius of 1.5 AU, but this is inside the horizon, the star is swallowed. If periapsis is well outside the horizon, say 10,000 AU, tidal forces are far too weak to disrupt the star. There's no intermediate regime where tidal disruption produces observable signals. This means Holmberg 15A's black hole, despite its enormous mass, rarely produces tidal disruption events observable from Earth. The rate of TDEs depends on the stellar density near the black hole and on the dynamical processes that scatter stars onto plunging orbits. For Holmberg 15, A, the large core, means stellar density near the black hole is low, reducing the TDE rate. Estimates suggest TDEs might occur once per 100,000 to million years, compared to rates of once per 10,000 to 100,000 years for typical supermassive black holes. When TDEs do occur in galaxies with ultramassive black holes, they're spectacular. The disrupted star forms an accretion disk around the black hole, and accretion produces a luminous flare lasting months to years. These flares are bright enough to be detected across cosmological distances, and surveys, like the Zwicky Transient Facility and the upcoming Vera C. Rubin Observatory, will monitor for such events. Detecting TDEs in galaxies like Holmberg 15A would provide rare opportunities to study accretion onto ultramassive black holes. For stars that do survive encounters with Holmberg 15A's black hole passing close without being disrupted or swallowed, the effects are still dramatic. The star experiences extreme gravitational forces that can strip away outer layers, reducing its mass. The encounter also changes the star's orbit, potentially flinging it out of the galaxy entirely as a hypervelocity star. Observations of the stellar population near Holmberg 15A might reveal evidence for such processed stars, though disentangling these signatures from other effects is challenging. Holmberg's legacy: the astronomer who catalogued hundreds of galaxies. Erik Holmberg, the Swedish astronomer after whom Holmberg 15A is named, played a quiet but important role in 20th century astronomy through his systematic cataloguing of galaxies. Born in 1908 inches Sweden, Holmberg studied astronomy at Uppsala University, receiving his PhD in 1937 with a dissertation on the properties of double and multiple galaxies. His career spanned the transformative era when extragalactic astronomy evolved from a fledgling field into a major branch of astrophysics. Holmberg's primary contribution was his photographic survey of galaxies, conducted over nearly 2 decades from the 1,930 seconds through the 1,950 seconds. Using telescopes at Uppsala Observatory and other facilities, he photographed hundreds of galaxies, carefully measuring their brightnesses, sizes, colours, and morphologies. This work required immense patience and attention to detail. Each photographic plate had to be exposed for hours to capture faint galaxy light, then developed and analyzed. Holmberg measured galaxy properties directly from the plates using photometers and microdensitometers, instruments that measured the darkness of the photographic emulsion. The catalogue Holmberg, published in 1950, contained 497 galaxies, each with measured properties and notes on morphology and companion galaxies. The catalogue wasn't complete in any volume-limited sense. Rather, it sampled galaxies of various types and distances to enable statistical studies of galaxy properties. Holmberg was particularly interested in binary and multiple galaxy systems, recognizing that studying interacting galaxies could reveal important information about galaxy masses and dynamics. One of Holmberg's notable achievements was pioneering the use of analog experiments to model galaxy interactions. In the 1940 seconds, before electronic computers were available for astronomical calculations, Holmberg constructed a physical analog of gravitating systems using light bulbs and photocells. Each light bulb represented a star or mass element, and the inverse square law of light intensity mimicked the inverse square law of gravity. By measuring the light intensity at each location from all the bulbs, he could calculate the gravitational force at that location. Moving the bulbs according to these forces and iterating the process simulated the gravitational dynamics of interacting galaxies. These analog experiments, crude by modern standards, produced qualitatively correct results, showing how tidal forces could distort galaxies during close encounters. Holmberg published results predicting tidal tails and bridges in merging galaxies, features that were subsequently observed in real galaxy pairs. His work anticipated by decades the detailed n-body simulations that became possible with computers in the 1970 seconds and later. Holmberg also contributed to understanding galaxy luminosity functions, the distribution of galaxy brightnesses. By analyzing his catalogue and relating galaxy brightnesses to distances estimated from redshifts, he derived early estimates of the galaxy luminosity function. This work helped establish that galaxies span an enormous range in luminosity, from dwarf galaxies thousands of times fainter than the Milky Way, to giant ellipticals like Holmberg 15A that are tens of times more luminous. Throughout his career, Holmberg maintained a focus on careful, systematic, observational work rather than pursuing the most glamorous or high-profile projects. His catalogue, while eventually superseded by larger modern surveys, was an important resource for decades and contributed to numerous studies of galaxy properties and evolution. The fact that one of the most extreme objects in the universe, the galaxy hosting the largest known black hole, bears his name in the form of Holmberg 15. A serves as a fitting tribute to his contributions. Holmberg retired from Uppsala University in 1975 and passed away in 2000 at age 92, having witnessed astronomy's transformation from a field based on photographic plates and analog calculations to one based on electronic detectors and supercomputers. His catalogue and his careful observational work helped build the foundation for modern extragalactic astronomy, and the objects he catalogued continue to be studied with increasingly sophisticated techniques by new generations of astronomers. Future observations, JWST, and the next generation of black hole studies. The James Webb Space Telescope, launched in December 2021, represents a quantum leap in observational capabilities for studying distant galaxies and their black holes. With its 6.5-meter segmented primary mirror and suite of near to mid-infrared instruments, JWST can observe objects far fainter and more distant than previous facilities. While JWST's wavelength coverage is optimized for detecting high redshift galaxies in the early universe, it also enables unprecedented studies of galaxies like Holmberg 15A in the nearby universe. For Holmberg 15A specifically, JWST's high spatial resolution, approaching 0.03 arcseconds in the near-infrared, could resolve structures in the galaxy's core at scales of roughly 100 light-years. This is significantly better than ground-based observations and could reveal fine-scale features in the stellar distribution shaped by the black hole's influence. JWST's sensitivity to old stellar populations in the near-infrared makes it ideal for studying the evolved stars that dominate Holmberg 15A's light. JWST observations could also search for dust and molecular gas in Holmberg 15A's central region. Mid-infrared imaging and spectroscopy are sensitive to warm dust heated by starlight or by weak accretion onto the black hole. Detecting such dust would provide insights into whether any fuel for black hole accretion exists in the nucleus. Most massive ellipticals have very little cold gas, but even trace amounts could affect the black hole's current and future accretion. Beyond Holmberg 15, a JWST will contribute to understanding ultramassive black holes by enabling studies of more distant analogues. BCGs in clusters at redshifts of 0.5 to 1, corresponding to look-back times of 5 to 8 billion years, can be observed in detail with JWST. Comparing the properties of these earlier epoch BCGs to present-day ones like Holmberg 15A reveals how these systems have evolved over cosmic time, including how their black holes have grown. Ground-based, extremely large telescopes currently under construction will complement JWST with higher spatial resolution at optical wavelengths. The Extremely Large Telescope, or ELT, in Chile, with a 39-meter primary mirror, will achieve spatial resolution of 0.001 arcseconds with adaptive optics, over 10 times better than current 8 to 10-meter telescopes. The Giant Magellan Telescope and 30-meter telescope, with effective apertures of 25 to 30 meters, will provide similar capabilities. These ELTs will enable stellar, dynamical studies of black holes in more distant galaxies than currently possible. For Holmberg 15A, at 700 million light-years, ELTs could map velocity dispersions with spatial resolution better than 100 light-years, significantly improving black hole mass measurements. For galaxies at distances of several billion light-years, ELTs will enable the first resolved stellar dynamical measurements, expanding the sample of precisely measured black hole masses. Gravitational wave astronomy will mature over the next decades with improved pulsar timing arrays and the launch of LISA. PTAs with 30-year baselines and timing precision, improved by an order of magnitude, could detect individual nearby supermassive black hole binaries in the final years before merger. LISA will detect mergers of intermediate mass black holes and possibly smaller supermassive black holes at cosmological distances, providing a complementary view of the black hole population. Multi-messenger observations combining electromagnetic, gravitational wave, and possibly neutrino detections will provide the most complete picture of black hole mergers and accretion processes. Coordinated campaigns monitoring galaxies undergoing mergers with electromagnetic telescopes while listening for gravitational waves with PTAs or LISA could catch mergers in action. Such observations would constrain merger timescales, black hole spins, and the energy released through different channels. X-ray astronomy will advance with next-generation missions like Athena, ESA's Advanced Telescope for High-Energy Astrophysics, planned for the 2030 seconds. Athena will have far greater sensitivity and spectral resolution than current X-ray telescopes, enabling detailed studies of hot gas in galaxy clusters and weak X-ray emission from quiescent black holes. For Holmberg 15a, Athena could potentially detect faint X-ray emission from hot gas very close to the black hole, providing insights into the accretion flow. Radio astronomy will see dramatic advances with the Square Kilometre Array, or SKA, currently being constructed in Australia and South Africa. With effective collecting area of 1 square kilometre and sensitivity orders of magnitude better than existing facilities, SKA will detect faint radio emission from jets and accretion flows around supermassive black holes. For Holmberg 15, a SKA could detect radio emission from any low-level jet activity and map the distribution of relativistic particles in the galaxy's halo. The Next Generation Event Horizon Telescope, with additional stations and higher observing frequencies, may eventually achieve angular resolution sufficient to resolve the event horizons of a few ultramassive black holes beyond M87. While Holmberg 15a is likely too distant and its black hole too faint for direct event horizon imaging in the foreseeable future, other nearby ultramassive black holes could become accessible. Such observations would provide the ultimate test of general relativity's predictions for event horizon structure and black hole spin. What Holmberg 15a teaches us about the universe's largest structures. Holmberg 15a and its ultramassive black hole represent an extreme but not unique example of cosmic structure formation. Studying this system teaches us fundamental lessons about how structures form and evolve in the universe, from the smallest scales of stellar systems to the largest scales of galaxy clusters. The existence of such massive black holes pushes our theories to their limits and tests whether our understanding of gravity, black hole physics, and structure formation is correct. First, Holmberg 15a demonstrates that hierarchical structure formation, the bottom-up assembly of larger structures from smaller ones, works across enormous scales. The galaxy itself formed through mergers of smaller galaxies over billions of years. Its black hole grew through a combination of accretion and mergers with other black holes. The Abell 85 cluster formed through the merger of smaller groups of galaxies. This hierarchical assembly, predicted by cold dark matter cosmology, has been confirmed through observations of galaxy evolution, and Holmberg 15a represents one of the end points of this process. Second, the system illustrates the tight connection between galaxies and their central black holes. The relationship between black hole mass and galaxy properties, including stellar mass, velocity, dispersion, and luminosity, holds even at the extreme masses represented by Holmberg 15a. This suggests that black holes and galaxies evolve together through shared processes, likely involving feedback where black hole activity regulates galaxy growth and vice versa. Understanding this co-evolution is crucial for understanding why galaxies have the properties they do. Third, Holmberg 15a shows that black hole growth can proceed far beyond what's possible through gas accretion alone. The 40 billion solar mass black hole could not have formed through steady accretion starting from stellar mass seeds, even under optimistic assumptions. Mergers with other supermassive black holes must have played a dominant role. This demonstrates the importance of galaxy mergers in building the most massive black holes and shows that merger-driven growth is a distinct channel from accretion-driven growth. Fourth, the quiescent state of Holmberg 15a's black hole illustrates that most supermassive black holes spend most of their time accreting slowly or not at all. The quasar phase, when black holes accrete vigorously and shine brightly, is episodic and represents only a small fraction of cosmic time. Most of the black hole mass in the universe today resides in quiescent systems like Holmberg 15a rather than in actively accreting quasars. This has important implications for understanding the energy budget of the universe and the role of black holes in galaxy evolution. Fifth, the large core in Holmberg 15A provides direct observational evidence for the final parsec problem and its resolution. Binary black holes can stall at separations of roughly a parsec unless additional processes enable further hardening. The fact that Holmberg 15A has a large core indicates that binary black holes did eventually merge, overcoming the final parsec problem through some combination of stellar scattering, gas talks, or other mechanisms. This confirms theoretical expectations and validates simulations of binary evolution. Sixth, Holmberg 15A and similar systems provide natural laboratories for testing general relativity in extreme conditions. Near an ultramassive black hole, space-time curvature is so strong that relativistic effects dominate orbital dynamics. Future observations measuring stellar orbits very close to the black hole could test predictions of general relativity, including frame dragging, light bending, and gravitational redshift. Any deviations from general relativity's predictions would indicate new physics or modifications to gravity. Finally, Holmberg 15A reminds us that the universe is capable of producing structures more extreme than we might naively expect. Before discovering ultramassive black holes, theorists debated whether black holes exceeding 10 to 20 billion solar masses could form. Holmberg 15A shows unequivocally that they can. This suggests our theories are on the right track, but that nature can push to greater extremes than simple models predict. The existence of such extreme objects challenges us to refine our theories and to search for even more extreme examples that might exist but haven't yet been found. Looking to the future, Holmberg 15A will remain an important target for observations across the electromagnetic spectrum and will serve as a benchmark for theoretical models of black hole growth and galaxy evolution. As observational capabilities improve with new facilities like JWST, ELTs, and next-generation gravitational wave detectors, our understanding of this remarkable system will deepen, revealing new insights into the physics of the universe's most extreme objects. The discovery and study of Holmberg 15A's ultramassive black hole represents a triumph of modern observational astronomy and theoretical astrophysics. From Erich Holmberg's initial discovery of the galaxy in 1937 using photographic plates to the 2019 measurement of its 40 billion solar mass black hole using sophisticated dynamical modeling, the story spans nearly a century of astronomical progress. Every generation of astronomers has added new pieces to the puzzle, gradually revealing the extraordinary nature of this cosmic giant. The techniques developed to study Holmberg 15A, including high-resolution spectroscopy, Schwarzschild orbit modeling, and detailed analysis of galaxy cores, have become standard tools for characterizing supermassive black holes throughout the universe. The lessons learned from this system inform our understanding of black hole physics, galaxy evolution, and cosmology. And the questions raised by Holmberg 15A's properties, including how such massive black holes form and why they accrete so slowly despite their enormous masses, continue to drive theoretical research and observational campaigns. As we peer deeper into the universe with ever more powerful instruments, we may discover black holes even more massive than Holmberg 15A's, pushing the boundaries of what's possible for black hole growth. Or we may find that Holmberg 15A represents a true upper limit, determined by fundamental physics or by the cosmic environment in which black holes form. Either way, this remarkable object at the heart of a distant galaxy cluster will continue to captivate astronomers and to serve as a reminder of the incredible diversity and extremes present in our universe. The largest known black hole in existence stands as a testament to the power of gravity the violence of galaxy mergers, and the profound strangeness of the cosmos we inhabit.